In this video, we're going to take a look at the hypergeometric distribution. You're looking at one now. So let's begin by considering the parameters for this distribution. Look up here at the M. M is the population size. So to begin to understand this hypergeometric distribution, let's assume that our population is 20 students taking a risk course. D is the second parameter. D is the number of people in the population, or the number of items in a population that have the characteristic that's of interest to us. So let's let the characteristic that's of interest to us be being a woman. And let's assume there are 12 women in this class of 20. The third parameter is a sample size. In this case, it's 5. So what this distribution is showing you is if you take a sample of 5, these are the potential outcomes in terms of the number of women. We might get none, 1, 2, 3, 4, or 5 women in the sample. And notice that the probability of getting no women in a sample of 5 taken from a class of 20 people, where 12 of them are women, is very small. In fact, it's 0.4% chance that you'll see this value. So looking for zeros is going to be handy, as you'll see as the video continues. Here's the probability of getting one woman. It's slightly more than 5%. The probability of 2. 3 is the most likely outcome, the most likely number of women in a sample of 5. Here's 4 and here's 5. So now when I close this distribution, if you look up here in the upper left, as I hit the recalculate button, here's a 2, a sample of 5 to return 2 women. Recalculate, we get 3 women. Recalculate, 3 again. Recalculate, 4. Recalculate, 2. So each time I hit the recalculate button, this is showing me the result of a sample of 5 taken from a population of 20 where there are 12 women. So this distribution is really handy for looking for things in a population. Let's look at an application of that. Imagine that you are a country that is importing fruit from another country, and you import different numbers of boxes of fruit. So you might have a lot size of 500 boxes, 1,000, 2,000, or 5,000. Now let's imagine that you have a policy of taking a 2% sample from any lot size. Notice how the sample would vary. It would be 10 boxes in a lot size of 500. It would be 100 boxes in a lot size of 5,000. Now, let's suppose that we have a detection limit. We might be looking at rot or spoilage or infestation by some sort of pest or insect. And for the purposes of this example, let's assume that if that condition is 10% or less, if that rot or if that spoilage is 10% or less of all the fruit, that would be acceptable to us. So the number of detectable items that would be acceptable would be 10% of 500 or 50, and at the far right it would be 10% of 5,000 or 500. So now let's take a look at the hypergeometric distribution and see how this might help us. For this current example, notice the parameters. M is found in C3, that's the lot size. D, the characteristic of interest, is the number of detectable items, that's found in C7. N, the sample size, is found in C5. So this says in a sample of size 10, taken from a population of 500, where 10% of the population could be spoiled, these are the results that we would expect to see. it would be very unlikely to see 10 spoiled items in a sample of 10. The number that we're interested in, however, is 0. We would like to know the probability of no spoiled items in a sample of 10. Because no spoiled items is telling us what the likelihood is that we have no spoilage, or at least spoilage that is below our detection limit of 10%. So you'll notice here that 34.5% is the probability of obtaining no spoiled items in a sample of size 10, where 10% of all the items are indeed spoiled. So if I take the complement of that, 100% minus 34.5 gives me a 65.5% confidence limit, or confidence levels, excuse me, that I have a lot here that meets my detection limit or less. So I'm 65.5% confident that this lot has 10% or less of its fruit that is spoiled. So keep that number 65.5% in mind. That results from a 2% sample. If I take a 2% sample from a lot size of 1,000, then I get a different result. You'll notice there's an 11.9% chance of no spoiled fruit in those boxes. The complement of that is 88.1%. So I have a confidence level of over 88% that we have a lot here that meets our detection limit of 10% or less. That comes from a 2% sample. Here's another 2% sample of our lot size of 2,000, and here we see there's a 1.4% chance of 0 defects. That means we have a 98.6% confidence level that this lot will meet our detection limit of 10% or even less. And finally, for a lot size of 5,000, we see the probability of getting 0 defects in a sample of 100 is smaller than 0.0. So what that means is our confidence level is greater than 99% that we will meet the detection limit of 10% or less. Now what's interesting about this, and I understand this is hard to absorb, the hypergeometric distribution's use is not easy to imagine at first. But what's interesting about this is we take a sample size of 2% as a matter of policy, and we get widely varying confidence levels. 65%, 88%, 98%, and over 99%. What this is telling us is we are not sampling enough from small lot sizes. We don't have much confidence in the fact that we're meeting the detection limit, only 65%. Only 88% confidence that we're meeting the detection limit for a lot size of 1,000. So we're undersampling for those lot sizes. However, we have 98.6% confidence we're meeting the detection limit for a lot size of 2,000. And if, for example, we would be satisfied with a 95% confidence limit, which is fairly standard, then we're oversampling the large lot sizes. The same would be true for lot sizes of 5,000, where our confidence level is over 99%. So the hypergeometric distribution can be used to help us use risk-based sampling so that we can choose different sample sizes for different lot sizes. We can choose different sample sizes for different detection limits. So let's have a look at that now. Imagine that we have a detection limit of 0.1% and a lot size of 1,000. Then we're going to imagine a different detection limit, 1% for a lot size of 1,000, and a different detection limit of 10% for a lot size of 1,000. So let me show you how this might work before I show you the results. We're going to pull up a distribution. We're going to create a hypergeometric distribution. I'm going to put a population of 1,000 in here. Whoops, having a little trouble here. That was more difficult than it needed to be. And we're going to use a detection limit, let's say, of 10%. So that means we have 100 items that have the characteristic of interest. And we'll leave the sample size at 10% here. If we take a sample of size 10, then we have 1 minus this value here. And this value is 34.7%. So we have a 65.3% confidence level that we are meeting our detection limit. If I would like to have greater confidence in my sample results, I have to increase the sample size. Notice as I do so, watch this bar get smaller. When this bar gets down to 5%, that's when I'm 95% confident that we're meeting our detection limits. So you see the bar shrinking, getting smaller. Right now it's at 5.6%. That's not quite there. There we go, right at 5%. And that tells us if we would like to be 95% confident that we are meeting our detection limit of 10% in this example, we need a sample of size 28. So this is a handy way to use the hypergeometric. It tells us what sample size you need to obtain a certain level of confidence, like 95%, given a detection limit. So let's take a look now with a detection limit of 0.1%. I pull up my distribution. I have a population of 1,000, and I have one item that has the characteristic of interest, the defect in it. You'll notice here we need an extremely large distribution. An extremely large sample. We need to sample 950 boxes of fruit to be 95% sure that we have met the detection limit in our lot size of 0.1%. Now suppose we have a detection limit of 1%. We're willing to accept 1% flawed shipments. Here you'll notice when the sample size is 257, we have 95% confidence that we are meeting our detection limit. And if we have a detection limit of 10%, you will notice the same number we just derived a moment ago. We need a sample size of 28. So the hypergeometric distribution can help us decide how large a sample we need to take to achieve a certain detection limit. So if we are looking for diseases in animals, defects in imports, the number of defects in any kind of shipment at all, this is a really handy distribution to use. One last application. I've chosen a lot size here of 500, 1,000, and 5,000. And using a detection limit of 10%, it's not difficult to develop tables. If you would like 80% confidence in meeting that detection limit, you only need a sample of size 16. For 85% confidence level, a sample size of 18. 90% confidence level, a sample size of 22. And you'll notice you don't really get movement in the sample size until you increase the confidence levels significantly. So these are some uses of the hypergeometric. You'll have to spend a little bit of time with it. Use some analogies and figure out how you might be interested in using this. And feel free to ask questions in class.